Hello, welcome. Okay. So, last time we did series parallel combination circuits. There are a couple of things I want to kind of tidy up, a few loose details. So let's go ahead and let's see that. I'm going to start with a really useful circuit element. This is something that I use all the time, actually daily. This is called a voltage divider. And it's not just done for academic learning purposes. This is a circuit element that is in every single thing that I've done, whether it's an embedded system or other. I always end up using a voltage divider at one point. So this is one of those kind of special use cases where it is definitely worth it to remember and learn the formula that we're going to see here in a minute. So let's go ahead and let's talk about what this is. First off, I'm going to put the voltage divider up. And I'm going to go ahead and call this voltage source V in. We can just think of it as an input. One thing you're going to realize very quickly when it comes to embedded systems, FPGA development, any type of circuits, you tend to have like an input and you have an output. Whether that's an incoming signal, something like a temperature sensor, and then an output that goes into an embedded system, a microcontroller, an FPGA, something like that. So oftentimes it's useful to think about inputs and outputs. Okay, so for that reason, for this example, I'm going to go ahead and just call this V in, our voltage in. And then we're going to just have two resistors. It's really simple and straightforward. And right in between the two resistors that I'll label as R1 and R2, I'm going to call this V out. So we know how to solve this circuit. This is nothing difficult. It's just two resistors in series. We saw it, 2 lectures ago. But that being said, just sort of wrapping your mind around this idea that we have a voltage input and we have a voltage output is what's going to be different for us. Now, voltage divider, the primary reason that we would use this in a circuit element is that we have one voltage and we want a different voltage on the output. Okay, so what I'm going to do first off is actually just put up the general formula for a voltage divider, and then we're going to see that everything that we already know will get us to this equation. So V out is going to be equal to whatever V in is times the resistance of R2 divided by the resistance of R1 plus R2. And a good example of using this would be, let's say I have 5 volts out, but I actually want, let's say I have 5 volts in, but I actually want 2 volts to come out of here. And so how could we go ahead and set this up to do it? Well, we have two of our givens as far as this equation is concerned. We know what V out would be. We want it to be 2 volts. And we know that V in is 5 volts. And so we have two unknowns that we have to figure out, R1 and R2. And whenever you're in this situation, I'm just going to suggest pick one and then solve for the other one. So what I'm going to do in this case is I will pick one resistance and solve for the other. In this case, I'm going to go ahead and just pick R2 to be 100 ohms. So if I go ahead and make R2 now 100 ohms, well, now we just have an equation to solve for R1. And so from that perspective, it's really straightforward. V out equals V in times R2 divided by R1 plus R2. And in our case, two volts was our desired output. Our input that we were given or that we have to work with. And if you remember, or if you think about it, if you're working within a real circuit, you don't have all of these voltages available. You just need to like produce different voltages at times. When I use like 3 batteries in a design, each battery, let's just say, is a AA at 1.5 volts. And so I have 3 batteries. Well, that means I have, let's see, 4.5 volts in my circuit, but I may need 2 volts elsewhere or something along those lines. So I can go ahead and just say 2 volts is equal to 5 volts times 100 ohms, because R2, we picked it to be 100 ohms, divided by R1 plus 100 ohms. And so we find that R1 is equal to 150. So pretty much, if we have 5 volts out and we put 2 resistances in series with a 150 ohm and 100 ohms, in between the two, if we consider that to be our output, we are going to get 2 volts. So this ends up being very useful. This equation is one that I do have memorized, and I use it in 311 as well as my kind of daily job all the time. So this is one specialized equation that I'm going to say, remember. Okay, so in our example, we put in 5 volts and we get 2 volts out. Now, let's go ahead and I hate putting up an equation when I know that we can actually just solve for this very straightforward. So let's see how we can do that. So let's go back and do this symbolically. So I have a V in and a V out and an R1 and an R2. I am getting feedback from... Aha, perfect. Okay, the feedback's gone. Okay. So can we come up with that equation that we saw where V out is equal to V in times R2? So just for reference, we're trying to find this. V out is equal to V in times R2 divided by R1 plus R2. And obviously that's a given equation at this point, but let's go ahead and let's arrive at this just using our basic rules. So first thing to kind of notice is let's see what is V out equal to. Well, V out over here is just the voltage drop across R2, right? So that's the first thing that kind of stands out to me. So we can now reduce it in terms of V out being equal to VR2. Now, kind of the next rule we should look at is, well, it's a series circuit. Current's the same at every point in a series circuit, right? So I can go ahead and just say that this is the total current for the entire circuit. Now you may be looking at this wire and say, but hey, I got a branch where some current is going this way and some other current might be going this way. And although that could be true depending on whatever I connect at this point, but in this case, notice I don't have a path for current to go anywhere. So this wire can kind of just be seen as an appendage. It just has a voltage. It's a point that we're taking a voltage at. I don't have any resistors here with a path for current to go anywhere. So the current that we do have going through this wire really is zero. And so sometimes when I have zero and I want to explicitly say that I have zero current going through something, I'll just draw an arrow with an arrow on both sides and I'll call it 0 amps. So we have zero current going in or out here. So even if you were to look at Kirchhoff's current law over here, the current going through R1 is still equal to the current going through R2 because there is no current on this wire going in any direction. Okay, so we can go ahead and say for what I did in step 2 is that I is the same for all components in series. Okay, so that kind of gets us pretty well set up. Now, we should also, let's see, at this point, I'm trying to write an equation for V out in terms of R1, R2, and V in. That is my goal here. So can I go ahead and use Ohm's law at this point? Absolutely. So V out is equal to VR2. We already know that. And what's VR2 equal to? Well, the voltage drop, if VR2 is the voltage drop across R2, and that's what V out is equal to, then I can just use Ohm's law and say that VR2 is equal to IT times R2, right? The current going through R2 times the resistance of R2 gives us the voltage drop across R2. So it's just a straightforward application of Ohm's law here. Where V out is equal to VR2. VR2 is equal to IT times R2. Now, what we still need to do, though, is we need to define IT. Because again, I'm trying to write this equation in terms of V in, R1, and R2. There's nothing about IT in here. So I need to go ahead and explicitly solve for what IT would be equal to in this circuit. So in this case, we can just use Ohm's law again. And we know that for this circuit, I can reduce this circuit so that it is just one resistance that's equal to R1 and R2 in series. So I can go ahead and I can say that IT is equal to the applied voltage divided by the total resistance, where the total resistance is just equal to R1 plus R2. So now if we go ahead and put these two together, we can say that IT is equal to Vn divided by R1 plus R2. Right? I just plugged in what RT was for this circuit into RT. That gives us our total current. So now I have the total current defined as Vn over R1 and R2. So we're actually almost there. All we need to do is plug that into what V out is, and we'll get a function for V out. So let's say we plug 2 into 1, right? Plug the second equation we found into our first equation, and we should get what V out is in terms of just V in and R1 and R2. So we end up with the same equation that I gave in the first place, right? So just our basic rules were enough to derive this equation, and this equation, I will say, is useful enough to merit remembering it for the rest of your lives. This is something that just pops up so often. Okay, so there's a very useful application of a very simple series circuit that we just use it all the time. Okay, so that's it for voltage dividers. I'm going to move on to a couple of other things that we should mention before we continue with more of our series parallel circuits. I should ask, are there any questions in regards to this voltage divider? Why does V out have no current? Because I don't have anything attached to it. Now, all bets are off with this equation as soon as we do something with this. Would it be like a ground? No, not at all. This would not be at all like ground. If I were to go ahead and attach something to this voltage divider, let's just say I had 5 volts and I had 2 volts, just like the example we solved previously. If I went ahead and I attach something that's going to actually draw current from it, now our previous equation actually becomes not applicable, because now I have RL, the load, and when I use load, this is to signify something that is drawing a good amount of current. So a load, something like an LED, a microcontroller, or if you want to go bigger, your light bulb in the house. All of these can be considered loads. They just act like some resistance drawing some amount of current. So RL tends to be a stand-in that we use all the time in circuits to represent something that is drawing current, something that has power being dissipated. And so if I were to attach this, now I'd have to recalculate the equation, but take R2 and RL to be in parallel. So now that begs the question, is like, well, why should I memorize this equation if the second that I attach something to it, all of a sudden all bets are off with that equation? And I would say that there are many times that we actually attach things to a voltage divider like this that actually use zero current. All they do is look at the voltage over here. So we have plenty of circuit elements. If you think about connecting to an input on a microcontroller, like from 262 class or 346, or you think about even connecting to an FPGA from like 201, 301, etc. Those pins on the actual integrated circuit, the computer chip, actually use very little to no current, or we can consider it at the very least to be negligible. And so there's plenty of times, actually more often than not, the things that we do attach to a voltage divider end up using little to no current, or if it does use current, it's in the microamps. So it's so small we don't even have to bother calculating it, which is kind of nice. But no, it would definitely, this point is not at all acting like a ground. Remember, our ground should be at the negative terminal of our voltage source. So if you wanted to specify a ground for this circuit, this is the point that would make the most sense. This would be your 0 volts, and we start off, say, if this was 5 volts, you start out at 5 volts, you drop. In this case, if it was our example where we had 2 volts here, we have to drop 3 volts across R1, and then we drop 2 volts across R2. Hopefully that answers. Any other questions? Okay, let's go ahead and let's talk about putting multiple voltage sources in series. So, there's no reason that I can't do something like this, where I connect the minus sign of one voltage source, we can call it V1, and I connect the minus sign of this voltage source to the positive of another voltage source. In fact, this is what happens. Like if you look at a remote control and you see 2 batteries, this is exactly what they're doing. And so if I go ahead and use that example, if I use, let's say my remote control where you have 2 AA batteries in the back, well, one of them is 1.5 volts and the other one is also 1.5 volts. Let's just say they're two times AA batteries. This is exactly what they're doing here. They want a higher voltage, and each cell, each battery can only produce 1.5. So what they do is they put them in series, and when we do this, it is referred to as series aiding. And the reason they call it aiding is because both of these voltages are actually going to add up. So if I go ahead and let's just say I set up an example, and I'm going to go ahead and use two different voltage sources. I'm not going to use the two 1.5 volts. You'll see why. Let's say this first one is 12 volts. And let's say this bottom one is 6 volts. And let's go ahead and say this R1. What does VR1 equal to? Well, according to what I wrote up here, these two should add up, and that would be the total applied voltage to this resistance. So in the case of 12 volts and 6 volts, they're going to be series aiding. So I should get 18 volts applied to it. And I think the best way to illustrate this is actually just to write out a KVL expression to show it. Now, KVL, or Kirchhoff's voltage law, says that for any closed loop, the sum of all voltage drops should be equal to 0, right? So let's go ahead and let's start over here. Keep in mind, this is not a current arrow. This is just to specify the voltage drops in this closed circuit here. Well, how do we go ahead and write out this KVL expression? It's the same thing I've been doing before. Let's first look at our polarities. These two are given, positive here, minus here, positive here, minus here. And if what I'm saying is true, we know that the current should go down through this resistor, R1. And so current always goes from a higher voltage to a lower voltage. So that gives me a good idea of my polarity that's being applied to this resistance. You can also think about it, the positives here and the positives connected to the resistance. Therefore, this should be a positive. And same thing down here, the minus here is connected to this side. So this should be lower voltage. And if I go ahead and start at this point and I follow this entire loop and write out the KVL expression, well, I keep going around. I hit the positive first, so plus 18. Keep on going, keep on going. I hit the next component, my 6 volt voltage source, and I hit the minus side first, so minus 6. Keep on going. I now hit my 12 volt source, and I hit that minus sign first, so minus 12 volts. And I'm back at where I started, so set the whole equation equal to 0. The sum of all voltage drops in any closed loop should be equal to 0. And sure enough, 18 minus 6 gives us 12, and 12 minus 12 equals 0. So Kirchhoff is happy, and this completely agrees with him. So this is a good example of series aiding, and it is commonly done all the time in order to get a larger voltage than what your voltage sources have. So if you have, if I needed, say, 9 volts in my circuit, let's say I needed 9 volts for some device that I'm making, and all I have is AA batteries. Well, 2 batteries is going to give me 3 volts. 4 batteries would give me 6 volts. And 6 batteries would give me 9 volts. So I would actually need to put 6 AA batteries in series. It's a lot of voltage sources I'm writing here. 1, 2, 3, 4, 5, 6. Okay, and I have all of their polarities such that the positives are all attached to the minuses. Okay, and you might go, well, this looks ridiculous on a schematic. And I would agree. So they use a shorthand for these voltage sources. Instead of putting 4 lines, they actually just use 2. So we have 1, 2, 3, 4, 5, and 6. I put in an extra one. Oh, I gotta redraw that. That looks awful. Okay, 1, 2, 3, 4, 5, 6. And this is done all the time. Many devices, when you're putting in 6 batteries into something, like a great example, I have this label maker over here. Now it looks like this label maker just has 3 batteries, but check this out. There's another battery behind each one of these. So this one's got 6 batteries, and this is exactly what they're doing. Reason for that is the motor on this guy needs that higher voltage, needs 9 volts. So that's exactly why they do this. So this is a great example of where they're doing series aiding in order to get that higher voltage that they need for their device. So in this case, this label maker actually runs off of 9 volts. Now, not that this is commonly done, however, it can be done. Series opposing, where we actually reverse one of those batteries so that one is applying the electromotive force in one direction and then the other battery is kind of backwards and actually negating some of that electromotive force. So let's go ahead and let's see that. When we do that, it's called series opposing. I'm going to redraw that. One too many lines. There we go. Okay, so in this case, this first voltage, V1, let's call it, has a plus up here, minus down there. The plus always goes to the larger bar. And for our V2, if you notice, this is now flipped upside down, positive on the bottom, minus at the top. Now, in this case, we can say that the total voltage is equal to the subtraction of the two of them. So we could say VT equals V1 minus V2. But then it gets a little confusing sometimes, because if V2 ends up being larger than V1, well, then we end up with a negative voltage. And there's nothing wrong with a negative voltage. I just try to avoid negative signs whenever possible. So let me go ahead and say this that might help. So subtract the voltages. And the result is polarized in the direction of the greater source. So let's go ahead and let's do a couple examples of this. Let's start out with an easy one. So what's VT going to be equal to? Well, if we think about it, and I think the best way to think about this is think about this as a vector. Think about this voltage as not just having a magnitude, but having a direction. So this V1 is actually pushing the electrons with some magnitude, 12 volts, in this direction. Okay, and so this is kind of like our conventional current, right? We're pushing the electrons in this direction. And maybe I shouldn't use the word electron in this case. We're pushing the current in this direction, okay? Conventional current with some magnitude of 12. And then look at this bottom voltage source is pushing with a magnitude half of this first one in a downward direction because its polarity is flipped. And if you go ahead and add up the vectors, what you end up with is 6 volts pushing in an upward direction. Okay, so that's kind of exactly what I said here. Subtract the voltages and the result is polarized in the direction of the greater source. The greater source in this example is this V1 equals 12 volts. I just subtract 6 from it because this one's going in the other direction, and I end up with a result of 6 volts, but the polarity is the same as the greater source. Okay, so just a couple of different ways to think about this. You can think of it as 2 vectors, or you can just go ahead and remember to do this, whatever works best for you. So that's kind of our series opposing. This tends to not be as useful because you're wasting some power to do this, because you're basically using this voltage source in order to cancel out this voltage source. You would just use a smaller battery. Yeah. Let me go ahead and flip the two. I'm going to reuse that sheet that I messed up on. Okay, so let's go ahead and let's set up the same thing. And V1, I will make this one to be 6 volts. And V2 can be equal to 12 volts. And I'm not going to draw it just yet, but notice what's happening here. This V2 over here is applying the electromotive force 12 volts in a downward direction because our positive's on the bottom. And so if you think about the conventional current, that's pushing downward with a magnitude of 12. However, the top voltage source is canceling out some of that. Half of this in an upward direction of 6. And so which one's going to win? Well, it's going to be this 12-volt source down here. This is only canceling out 6 volts of push from the bottom one. The bottom one's trying to push 12 volts down. This top one is canceling out 6 volts of that. So our result ends up being polarized such that we have the positive on the bottom, the minus on the top, and the combined EMF, or the combined voltage, is 6 volts. Does that kind of make sense? Okay, so series aiding, series opposing, and we also covered voltage dividers earlier. Let's go ahead and do another topic. Shorts. Not the ones I'm currently wearing, but short circuits. Shorts usually are unwanted low resistance paths in a circuit. And you actually have a couple of these in the lab from last time. That's why I said that you wouldn't be able to solve some of those until you saw this topic today. Okay, so we would go ahead and define a short as a usually undesired, very low resistance path in a circuit. I say usually because maybe you do want a short. I don't know. However, I can say that probably most everyone here throughout your academic career, you're going to never want these in your circuit. Okay, so let's go ahead and draw what this looks like from a schematic perspective. Say I got a 10-volt source. And I hook it up to R1. This is our very simple heater circuit. And now, let's say I set this up as a real circuit. Let's say we refer to this as breadboarding for prototyping our circuits. I got a couple examples laying around here. I'll pull that up. Okay, so here's a perfect example of some circuit that I have made on my board. And let's say I'm going to measure some voltage. This is my multimeter. Multimeters are used for measuring voltage, ohms, and current. And to measure, I'm going to have to start probing this, but let's just say I'm not paying attention, and I go, and then I end up shorting. I add this wire from one side of a component to another side, and I accidentally touch those wires. And when you have a complicated circuit like something over here, it's not difficult to do. You're probing and you end up moving something, and next thing you know, you end up adding this undesired wire in here. Okay, this undesired very low resistance path. Okay, this wire is very low. It should be 0 ohms if we're talking about a theoretical sense on a board. In actuality, every wire has some itty bit of resistance. Resistance is a property. Resistor is a component. But regardless of how we get this, maybe we hook up something incorrectly, maybe we probe incorrectly, or maybe we just drop the thing and then something kind of bends over and makes this contact. Oftentimes, I'm using tweezers in order to work on something. And yeah, this is metal, and this can definitely make a bad connection in here. So what exactly happens when we get this very low resistance path in a circuit? Well, what ends up happening is effectively this short in parallel with any component is going to remove that component from the circuit. So let's go ahead and say when the short occurs, all the current I just can't spell today. Disappears. Okay, so when the short occurs, all the current ends up going through this short. And effectively, this resistor disappears. In fact, a short will effectively remove any component from a circuit. Now, the caveat is it'll remove whatever is in parallel with the short. Okay, so anything in parallel with the short ends up getting removed. Okay, so let's go ahead and let's set up some examples over here. So if all the current ends up going through this short, then what's the resistance in this circuit? Well, it goes to 0. So what does I end up being in this circuit? Well, apparently mathematically undefined. It goes to infinity. A lot of amps. Right? With 0 ohms in our circuit, we're essentially, we are connecting one side of the battery directly to itself. And if you've ever done this, like you take 9-volt batteries, 2 of them, and you plug them into each other, they start to warm up really hot and they end up just breaking because they are drawing as much current as they possibly can. And so, there will be some limitation. You can't get infinite amps. Something's going to give. The battery itself has a little bit of resistance, not theoretically on a piece of paper, but in real life, your battery will end up limiting the current to some very high amount. If it's a lithium battery, it'll just explode on you. You ever hear of a lithium battery catching fire? That's how that happens. That's why lithium batteries being so volatile with how they, if you puncture them or draw too much current from them, they swell up, and then the problem cascades, gets even worse, and then they catch fire. So they actually build little current limiting safety circuits and fuses into the batteries themselves, just so that they don't catch fire. But yeah, this is definitely a bad situation to be in. Now, what does this look like from kind of a mathematical point of view? Well, we do have two resistors in series, essentially over here. One of them is 0 ohms, and the other one is 100 ohms. So if I wanted to treat this like a total resistance, I could go ahead and say R1 times R2. Divided by 0 ohms plus 100. Well, at the top, the numerator ends up getting 0, and anything that you try to divide into it is going to end up giving you 0. So it definitely works with all of our rules that we've done. Is volts or current the one that kills? I have a video that I can point you to on that subject. Have you seen the video? Does anyone know the video I'm referring to? It's by a YouTuber named Boom. I'm going to pull it up for everyone. Well, actually, by pull it up for everyone, I'm going to send out a link for it.
Hi there. After all the videos I made, there are some people out there that just don't get it and say it's the current that kills, not the voltage. To prove it to you once and for all, I'll be using my power supply here connected to these wires. This power supply can generate 20 volts, 150... Yes, it generates 20 volts and 150 amps. Let's short it in a more controlled manner. Well, you see when I short it, the voltage goes almost to... I was saying, when you short it together, the voltage you can see goes to 0 and the current goes to 150. It's hot.
Out of curiosity, can you guys hear that? Oh, okay, good.
The power supply is set to 20 volts and I'm holding the wires with my fingers. I can't even weld with this power supply. Although this power supply can generate huge amounts of current, it can't send it through my body because it's only set to 20 volts. I can't even feel it on my fingers. I like to put it on my tongue, but before that, I have to reduce the voltage to something like 1 volt because, the resistance of the tongue is much smaller than the skin. And still, if I short the power supply, I get the same 150 amps. Okay, you can see it still sparks. Let's try it out. What the f? I thought I set it to 1 volt. Huge. Don't completely trust the gauges on your instruments and always double check them with a meter. Now, if I short the wires, I still get the same 150 amps. And it makes sparks, but the sparks are smaller because the voltage is smaller and therefore the total power is smaller. Let's put it on my tongue. See? Nothing. Let me explain. The simplest electrical formula is that voltage is equal to current times resistance. So if the voltage is 1 volt and if the resistance of my tongue is 10,000 ohms, then the current through my tongue will be only 0.1 milliamps. In order to create 1 amps through my tongue, I'll need 1 times 10,000 ohms or 10,000 volts across my tongue. See, the voltage is the energy required to create current. In order to get hurt, you need enough current. And to have enough current, you need high enough voltage. Anything that moves, including the electrons, started moving because some sort of energy has made it move. You will not have current without the voltage, at least in room temperatures. I don't know what kind of diabolical mumbo jumbo will happen at absolute zero. Saying that the voltage doesn't kill is like saying that the earthquake in the middle of the ocean doesn't kill, it's the tsunami afterwards that kills. With that analogy, if I shoot you, it's not my fault, it's the bullet's fault. This just in. Bullet.
Okay, so that's actually I like his videos. He does a great job of being quite humorous while also putting in a lot of good legit electrical information. There is another, since we're on this topic. EEV blog is also a great another one of the YouTubers out there, and he's quite good as well, and he's a great electrical engineer. So he puts out a lot of good videos, everything from teardowns and Fundamental Friday videos to people sending him weird electronics, and he goes into it. But there's a lot of good information over there too. Okay. So, getting back to shorts, let's go ahead and I'll do one more example of a short. So a short does not immediately mean that I'm going to get infinite current and I'm going to damage stuff. It is possible to have a short and actually still be in a safe condition. Let's say I have 10 volts applied to 200 ohm resistors. Well, what if I only short right there? So without the short, how much current do we have going through this circuit? IT is going to be equal to 10 volts divided by 200 ohms. And just so I don't mess up the basic math over here, I'll do 10 divided by 200 ohms. We get 50 milliamps. However, with the short, notice I've effectively removed this 100 ohm resistor from there. You could go ahead and consider this short to be in parallel with this 100 ohm resistance. And if these two are in parallel and this is 0 and this is 100, well, the total resistance we know is going to be 0 ohms for both of these. So you replace those with 0 ohms, or you think about this as just canceling out that resistance. And what we're left with is just 100 ohms in this circuit. So all of the current will end up going through that short, and what we're left with is with an IT equal to 10 volts divided by 100 ohms. And 10 volts divided by 100 ohms is 100 milliamps. Now, 100 milliamps is probably still safe for this circuit. So this is an example where a short doesn't always just lead to something breaking, but generally if this was an unwanted low resistance path, I could definitely get more current than I wanted to. Something could break in the circuit. Okay, so that's, are there any questions about shorts? Okay, so with that being said, well, we've covered voltage dividers, series aiding, series opposing, voltage sources in series in 2 different configurations, and we looked at shorts. So now you should be able to finish up that lab, and it is due next time. The date's posted on the website. So I'm going to do about a 10-minute break, and then I will be back. Okay, so let's say about 10:45. I'm not going to be recording the lab session. This is just a lab session to work on the lab. So I will be hanging around to answer questions, help anyone out. And if you have any questions about lab or anything that we've done thus far, I'm happy to address that. Or if you just want some side information on other things, I'm happy to talk about that too. All right. Take care, everyone, and I will see you in lab in about 10 minutes, 10:45.